super interesting trick. I don't know why it doesn't work, but it first example, let me try. Yes, trick heavy electrons. They don't radiate and like electrons, right? So basically, you can go to high energy and still be able to accelerate them in circles, which is extremely effective compared to accelerating in linear arrangement. And if in proton-proton coherence, the effective kind of parton electrons, muons, and taus, the full energy can be released in collision of these two particles. They are point-like positron. We can accelerate them. as you can follow Enrico Fermi idea and build accelerator on the Earth. But unfortunately, yeah, you should stop at some moment. So far, I'm just giving you very broad brushes. Okay, so anyway, put so far the most, I would say, obvious limitations. Power consumption less than 3 times power consumption of LHC, and cost less than 3-5 times LHC cost. So if that is indeed the limit, then see whether the color changes to red, right? So 40, 50 GeV for TeV, 60 TeV for muon colliders. And then at some moment, if you proceed further, cost becomes prohibitive, 5 times, 10 times LHC cost, and luminosity goes down as 1 over energy or 1 over energy squared, depending on you kind of care most. This is flux dilution factor. So question is, even if flux dilution factor, so far we even before 3 TeV collider, people haven't thought about that too much. Right now we believe that in addition to, there was only one way to how to treat that flux, put the machine deeper and deeper and deeper in the ground. So it means the exiting radius where the flux goes out of the Earth will be growing and growing and growing, and basically everything spreads over larger and larger and larger area. So now we believe that we need additional factor of dilution, because when it comes to approximately in the size, it's approximately that big. It's like half a meter. So you can imagine a lot of radiation coming half a meter, right, 30 kilometers away. It's like indeed like a needle, and it shoots through your body. Very unpleasant if you stay there for 365 days immobile, and that's what rabbits can do, right? So they'll be dying, right? So what we figured out that instead of keeping this flux, over half a meter of diameter on Earth somewhere there, we move the whole flux, because we know how to point muon beam up and down. Basically, that flux will be going over, for example, 10 meters of space, and you don't need to do it very often. Do it like once a day, every 5 hours, once a week, but slowly, kind of in each point where this flux exits the surface, move it back and forth. So it's sort of, we do it by changing the orbit. So very slowly by centimeters of the max. We can do it and forward. So that gives you a factor of dilution. So how much the area of this diluted flux compares to the area of the initial flux. So, and I put this dilution flux parameter like 1, 10, 100, 100, 100, basically 100,000 times in order to 1 over, energy cube or energy squared. That's 1 over energy, because we believe, we'll invent something in order to dilute that flux. For linear colliders, for example, plasma-based colliders, they can be really small, and I said gradients will be enormously long. Many limitations. First of all, yes, particles don't radiate when you accelerate them in linear fashion, right? If you don't try to bend them. But when they go through each other, electrons and positrons, they work like electromagnetic forces, right? And they focus each other. And electromagnetic force produced by opposite bunch are so strong that 100% of energy of your, for example, electron is radiated in the act of collision with another bunch, which is just 0.1 millimeter long, because that effect scales as energy squared, basically, and energy squared, and even already at 1, 3, 4, 5 TeV center of mass energy colliders, like click, 3 TeV click. In 3 TeV click, energy spread is 30%, RMS energy spread after just single act of collision with opposite bunch, right? And of course, 10 TeV are totally impossible. Basically, you will have, instead of nice point-like collisions, you will have a collision of your, for example, electron with a cloud of stuff, from energies up to the maximum energy to energies up to 0 energy, right? So one-time collisions are very inefficient power-wise, right? So because instead of circle colliders, you have many, many turns to collide. You need to put everything together and collide them and force them to collide. And right after that, all the power which you put in your beams goes into the beam dump. Basically, you're wasting the power. And if your power is limit, for example, 200 or 300 to 400 megawatt, that puts a limit on your luminosity, is 1 over energy, right? It becomes extremely long because the final focus systems get extremely long, extremely sensitive to jitters. In plasma, ultra-strong focusing hurts the staging, and it's impossible to accelerate positrons, unfortunately, in a plasma wake field. Many problems. So, if you look into the linear RF and plasma accelerators, you see that ILC, click are still affordable machines in terms of cost and power consumption, but already 10 TeV machines, I'm not talking about 30 TeV or 100 TeV machines, they become extremely expensive. For example, cost of this 1 PeV machine, 100 times LHC, right, in energy. So would be like 30 times cost of the LHC, $300 million, right? So some crazy ideas, which I do propaganda every so often, is when you forget about staging your plasma cells and accelerating a single kind of structure built of plasma, and that is the plasma in between the crystals. It's a crystal accelerator. Of course, that accelerator will support only muons because electrons will radiate immediately at such a high gradients of focusing and accelerating fields. And protons immediately interact with the crystal structure and will decay, but muons go through because the penetrating power of muons is very high. So basically, it's a wake field acceleration in a solid state plasma. If you know how to create solid state plasma out of your crystal, right, you can accelerate in crystals and get extremely high gradients, and kind of in 1 kilometer, you can get 1 PeV center of mass energy. But this is single crystal, essentially. It's a one crystal, single crystal. This right now, right? So, but you put 1 muon on one side in one channel, the part of the channel through the crystal, right? Another channel, and through the same channel, 2 particles get together and collide. Yes, you get low luminosities, but very high energies potentially with muons. Yes, and that's what I put here. Exotic colliders, yes, they can achieve extremely high energies. They can be short, but cost is unknown, and actually power consumption is, we know it will not be very small either. So if you put all together, to conclude, I'm limited in time. So the limits on electric power and cost already tell us where approximately we can expect problems with the power and cost. For circular proton-proton collider, it's about 50 to 70 TeV center of mass energy. For circular muon colliders, it's approximately, say, 30 to 50 TeV, right, where cost and power will become prohibitive. For linear plus and minus colliders, it's approximately at 3 to 5 TeV. For linear crystal colliders, yeah, it might be at the scale of PeV, but these colliders never been built yet, right? If you put everything together, that's what we have. For different colors represent circular, proton, circular, muon, linear, electron, linear. So that's where all these data points are. And of course, if power limited and cost is limited, so you stop somewhere, but you know that luminosity will go down if you increase the energy of these colliders. And cost, it becomes prohibitive somewhere here, even for the best colliders we can imagine, like muon colliders, circular muon colliders. Right, the summary. Colliders were a great story. Over 60 years, we built 31 of them, 7 operate right now, 2 are under construction. There are a number of plans in Europe, Asia, and the US for future colliders. HEP priorities for the next 2 decades seem to be construction of a Higgs factor, of Higgs factories, and do R&D over the next 2 decades on a 10 TeV plus muon collider. And ultimate colliders will be high energy but low luminosity by necessity. And that's what we believe. So for ultimate energy, of course, what matters, of course, is luminosity, power, and cost. Cost critically depends on core accelerated technology. Existing injectors infrastructure greatly help, and high energy usually means low luminosities. The limits for circular PP colliders is below 100 TeV. For circular E plus and minus, below half a TeV. For circular mu between 30 to 50 TeV. For linear and plasma linear accelerators between 3 to 10 TeV, and exotic crystal mu accelerators promise 100 TeV or low luminosity. So, but in any case, you see that muons, the most attractive options we see so far are heavy leptons, muons, and they seem to be particles of the future. So there's a bunch of references, and thank you very much for your attention. Sorry for taking too much time.
Thank you. Questions?
So was muon the chosen particle for you 10, 15 years ago?
Oh yeah, even more, let's say 30 years ago, say. Yeah. It was obvious. At that time, I was dreaming about like 100 GeV normal conductor RF collider called VLEP. or S-band, if you heard these names, S-band in Germany, VLAP in Russia. Later, our American colleagues similar type of accelerator, 100 GeV, center of mass energy, linear collider based on kind of X-band RF technology. In California, it was called NLC, Next Linear Collider. Was extremely attractive machine, would be built in late 90s easily, and Higgs would be discovered there, as we know for now, right? So with proper energy, if, you know, energy of collisions, you need like 250 GeV, right? So it would be cheaper at that time, faster, and very nice technology to explore, but it wasn't. Still, even at that time, it was, people knew that, you know, going too much beyond, you know, hundreds of GeV in linear colliders of very different types probably will not be feasible. So you need something circular. And we knew that for proton-proton machines, that will be, again, this disadvantage in complexity of a proton. Proton is complex object, right? So muon colliders, we even that time, the pioneers, one of them is here, Dave Neuffer, so, and Robert Palmer is another great kind of supporter of that idea for, I would say, 40 or 50 years. People knew, yeah, this is it. Right now, we just see their vision with better and better detail, right? Because of accelerator community, as I said, is 5,000 of great scientists and engineers. So they worked over all these years. So we know how to build, you know, modern machines of various types, modern light sources, modern colliders. And we know how much things cost, what it involves, and kind of we see that the vision becomes more and more focused that, yeah, it is feasible, but we also understand very well where the limit is. Limit for circular mu plus, mu minus colliders due to the, at least very basic factors, power, size, and things like 30, maximum 50 TeV. But it's still better than anything else you can propose right now. Better than any proton collider, but better than any electron collider. Any circular, linear, and so on. So muons are particles of the future, as it was stated many times. And we understand it now more clearly.
Can you go back to the summary slide with the various? Yeah, this one. So forget about cost. Let's say we become super rich. Forget about power consumption. Let's say we solve all our energy problems. Forget also about radiation. The biggest limitation I see here is that the region where you want to be, the luminosity has to go up. Otherwise, you don't do physics. And this tells you that whatever you do, you're probably limited
by power.
By, well,
power.
Because
power is the, again, the last, yes, cost doesn't matter, fine. But with the power, yeah, you can't afford spending all the power of, you know, city of New York for your collider, because it means that we become so important to society, more important than 20 million, you know, normal people. And so far the best is 1/3 of a city of Geneva. Basically, whatever the toys we are playing with, they shouldn't be more than the entire city of Geneva, which is 300, whatever, 400 population, right? $20 million size of, I'm not talking about Shanghai or Beijing, you know, it's impossible. Even Moscow, which is like 16 million, even, you know, 3 million. We play toys, and society sees that clearly. So question is, how expensive of a toy you can imagine. Even if toy is super expensive, but it requires so much energy, it will not be affordable. So the power is probably one of the fundamentals. At the same time, cost is interesting. You know, money is an interesting object, right, by itself, philosophically and in reality. But there is a lot of truth in that. How much you can give your kid for playing with, how much of a toy, right? So, and that tells you how important it for society. So if you see a clear goal why society should be convinced to spend 10 times or 100 times more than we spent already on LHC or other colliders, tell us what that reason. So it basically turns question back to you. Yeah, that might not be a limit, but so far we know that cost, because it's something fundamental, money is fundamental, tells you how much you need it for you. Your toy is important for the society. And the answer is, you don't know. Probably, yes. So the biggest instruments so far, again, this amongst sort of scientific instruments are what? International Space Station, $70 billion. And according to all the latest estimates in the US, the cost of ITER fusion machine, right, is $56 billion total. Of course, in Europe, it costs 20. US accounting is 56 to 65. These are the most expensive sort of scientific/technology toys afforded by society, and only because fusion is important for the energy, and energy is related to the power, which we are hungry, and there are limits, right? Nothing comparable we can offer as a scientist to the society to say, hey, we need 10 times more expensive toy. Factor of 2, yeah, maybe if your father is rich, right? So your country is rich, all right, but not factor of 10.
What I meant to say is that even increasing the cost will not drive you up in luminosity.
No.
Let's say, I mean, at 1 PV, you see at least, I don't know, 6 orders of
Right.
magnitude between what you need for the physics and what you have.
Yes, at 1 PV, you'll have, yeah, you need to
Because you want to,
here.
exactly, you want to be there.
Right, it's a 1, 2, 3, 4 to 5 orders of magnitude. Yes, and you should appreciate that this is probably the best you can hope for. These optimistic thoughts, reality could be much, meager. Yes, big discrepancy.
Which means we are planning the last collider now.
Or you figure out more. This, oh my God, particle, it's still a great discovery. Energy is 10 to the 21.
But there also the flux is a limitation, again, luminosity.
For the same sort of same reason, Mother Nature has some reason why they don't produce that many particles. They are not needed. Yes. Sure.
You mentioned some amount of GV per meter that you need to play to attain to do tau acceleration or muon acceleration, which essentially amounts to how fast you can manipulate this object. I made the math probably wrong. Nanoseconds are involved, but never mind. I made it wrong.
Yeah.
Can you say again what is the limitation in how fast you can manipulate the beam and bring it to speed so that you don't lose it anymore?
Again, you need particle realistic as soon as possible to increase the light. They like gamma, say 100 out very quickly, and that gives you average gradient. So what you get, tau of course leaves what how many seconds, right? So in order to get the max of the tau, whatever 3.1, 3.4 GeV, so it's 34 times more than mass of the muon, and you need to add that much energy in very short time, very short distance, right? So that's the limit on the minimum acceleration after which this object comes sort of reasonable. So heavier the particle, harder to do that, right? If particle is unstable, and we see that between taus and muons. So muons are, it's not easy still, but it's still reasonable time, tens of milliseconds, reasonable time for acceleration. Acceleration gradient per millimeter, per centimeter, per meter.
Did I catch it wrong? Did I catch it wrong that the plasma is doing 100 GV per meter?
Yep. Yeah,
so
plasma.
tau may be okay there.
Close to okay.
Of course, I'm dreaming.
Yes.
Okay.
Plasma. Actually, we are not far. One of the records I've shown you was 10 GeV over 30 centimeters. That's 0.3 meters. It's exactly 300 GeV. Am I right? No, it's 30 GeV. 30 GeV per meter, and you need 300. Basically, we are already almost within factor of 10. What is needed for tau? Factor of 10. What is needed for tau acceleration?
But better than several orders,
Oh yeah. But for muons, 3 MeV per meter, it's better. 30 years ago, it was a pretty serious gradient. Now it's peanuts. Essentially, you buy it off the shelf.
So going to what Dario was asking is the first, probably would be good to hear more about crystals. I don't know. This crystal option, you tell it very quickly, but in the end is what, the last.
Yeah. Again, yes. Crystals, because again, there are two factors there. The maximum gradient you can potentially excite is you fully separate electrons and ions in plasma. And that gradient, you can create a fully separated. All positives are here, all negatives are there, basically, when you create the bubble, right? The maximum gradient still is square root of density. That's why densities of current records is 10 to the 17, which is a millitorr. It's not an atmospheric plasma. Density is pretty low. In, of course, solid plasma, and potentially, have much higher gradient, order of like 1 T meter, 1,000. Right, but density is still high, and in high density plasmas, not many things can survive. Electrons will not go through, so protons also will nuclearly interact. So muons. But you still need to figure out how to excite the plasma. I told you that if you figured out how you can excite kind of gaseous plasma, low density gaseous plasma, effectively with lasers. So for plasma we are talking about here, for these multimode colliders, probably will be can be excited by like X-ray lasers or something like that. There are challenges how to separate for a very short moment of time. You need to separate electrons from ions, jerk them, right? And that requires power. And the power efficiency actually becomes interesting because it goes into the what is the limit for power consumption. Yeah, crystals interesting, but again, it's not even blue sky research. It's ultraviolet sky of ideas. In the world, what's the actual? I would say over the past 30 years, there were 5 names who published papers on that subject. I'm the last one. So previous one was Pizin Chen. Remember him, Dave? Pizin Chen, Toshi Tajima, Bob Noble. I forgot who else. Shapon Chattopadhyay and Vladimir Shiltsev. 6 names out of approximately like 50,000 people who worked over that time. Right, so it's 5 out of 50,000, 10 minus 4. So it's the very tail of the distribution of crazy scientists which do have time to think about great things. Yes.
Was true for everybody in the 50s and in the 60s.
Yes.
Whoever thought you could do beam collisions, you were
Right.
fool.
Right.
So
Comparable.
Okay, we are only half an hour late, which is kind of good. So I think we can thank you again.